This video is about types of solids. By the end of this video, you should be able to classify substances as one of the major types of solids, and you should be able to explain the properties of each type of solid in terms of particle behavior. Before we look at the major types of solids, let's differentiate between crystalline and amorphous solids. A crystalline solid is a solid where the atoms are arranged in an orderly, repeating 3D pattern. This is the most common type of solid and the type that we'll look at in this class. But it's also important to be aware of amorphous solids. In an amorphous solid, the particles are not arranged in an orderly fashion. In fact, the order is much like that in a liquid. However, the particles are stuck in place, so they can't flow like a liquid. Therefore, it's classified as a solid. Some common examples are rubber, glass, and obsidian. Again, we're going to focus on crystalline solids in this class. We're going to look at four major types of crystalline solids: metallic, ionic, covalent network, and molecular. Solids are characterized by the types of particles that exist at each lattice point. A lattice consists of a repeating cube. Each lattice point occurs at the corners of the cube, and in some cases at the center of the cube or in the middle of each face of the cube. These are three of the most common types of lattices. Let's start with metallic solids. A metallic solid must have a metal atom at each of its lattice points. Metallic solids actually exhibit a type of bonding we have not yet discussed. It's called metallic bonding. Let's consider what a model for metallic bonding must explain. A model must explain the fact that metals are malleable, meaning they can be poured into thin sheets, that they're ductile, able to be drawn into wires, that they're conductive of heat and electricity, that they're durable, and that they have high melting points. So a successful model will explain all of these things. Therefore, we conclude that metal bonds must be strong but non-directional. Strong meaning it's very hard to separate the metal atoms, but non-directional meaning it's easy to move them around. Looking at metallic bonding in more detail, we know that metals have a dearth of valence electrons. Therefore, they tend to form large groups of atoms that share electrons among them. We say that these electrons are delocalized. In other words, they don't just belong to the two atoms bonded together. Instead, they belong to many atoms in the group. Here we see examples of covalent bonding where the electrons are localized. They exist between the two atoms in the bond. And here we see metallic bonding, where the electrons are shared among many of the neighboring atoms. This way of thinking about bonding in metals is often called the sea of electrons model. Here we see the positive metal cations, represented in gray, surrounded by this blue sea of electrons that's both mobile and belongs to all of the atoms in the solid. The electrical and thermal conductivity, ductility, and malleability of metals is explained well by this model. So, in summary, metals are good conductors because their electrons are delocalized and free to move around. And metals are malleable and ductile because deforming the solid doesn't change the local environment around each metal nucleus. The atoms can move slightly. Another subcategory of metals is the alloy. An alloy is a combination of two or more elements, the majority of which are metals. Adding a second or third element changes the properties of the mixture to suit different purposes. Here you see a common list of alloys. For instance, you may be familiar with stainless steel. Stainless steel is primarily iron, but it also contains small amounts of carbon, chromium, and nickel. Iron, as you probably know, corrodes or rusts very easily. However, by adding carbon, chromium, and nickel, the stainless steel is able to resist this corrosion. There are two types of alloys: substitutional alloys and interstitial alloys. A substitutional alloy is where a second element takes the place of a metal atom. Here you see 14-karat gold. Some of the gold atoms have been replaced by silver atoms. They have literally been substituted for, making it a substitutional alloy. In an interstitial alloy, a second element fills the space in the lattice of the metal atoms, meaning smaller atoms are fit literally in between the existing atoms. Here we have iron atoms with tiny little carbon atoms stuck in between them to give us steel. For an interstitial alloy to be possible, the atoms must have significantly different radii. When the radii of the atoms is more similar, we'll get a substitutional alloy. Oxides are another common way of altering the surface of a metal or an alloy. Stainless steel contains chromium, which reacts with oxygen from the air to form a protective oxide layer. That reaction is shown here. This is beneficial since chromium oxide is inert or non-reactive, while iron oxide is active and promotes further rusting. So often, metals or alloys will be coated with a layer of oxide to prevent further reaction. Moving now to ionic solids. There are many different arrangements for ionic solids, but generally speaking, the larger anions are at each lattice point and smaller cations fit into the holes between the anions in a way that maximizes attractions between oppositely charged ions. Recall that ionic solids exist in a lattice that extends outward in all directions. This is why we use the term formula unit to describe the smallest whole number ratio of ions to one another, rather than molecule, since this unit repeats over and over again in the lattice. Considering ionic solids in the context of Coulomb's law once again, we see that different sized ions in an ionic compound minimize the distance between oppositely charged ions, which is favorable, while also keeping like-charged ions as far away from each other as possible. Another favorable thing. Recall again that as distance between opposite charges decreases, attractive forces increases. As distance between like charges decreases, repulsive forces increase. Now considering a model for ionic bonding that explains its properties. Ionic compounds have very low vapor pressures, high melting points, and high boiling points. This is due to the very strong Coulombic attraction between ions. Unlike in molecules where covalent bonds are not broken during melting, in an ionic solid, ionic bonds are broken during melting. The ions actually separate from one another. Due to their strong attraction, this requires very, very high temperatures. Ionic solids are brittle because like charges repel each other when layers slide over each other. Here we see this lineup of positives and negatives. If part of the solid is subjected to a sharp blow, positives end up lined up next to positives and negatives to negatives, causing repulsion. This causes the ionic solid to break apart easily. Ionic substances conduct electricity only when melted or dissolved, as we've seen with electrolytes, because ions are free to move when melted or dissolved, but not when in a solid. Recall we've seen this with the light bulb apparatus. Solid ionic substances do not light the light bulb. However, when we dissolve those ionic solids and allow the ions to be mobile, we can conduct electricity and light the light bulb. Our next type of solid is a network solid. This is a type of atomic solid because it has an atom at every lattice point. A network solid contains strong directional covalent bonds and can often be viewed as a giant molecule. In terms of properties, network solids are very brittle and usually poor conductors. Some common examples are carbon in the form of graphite or diamond, and silicon dioxide in the form of quartz. Here we see the structure of diamond and of graphite. Notice that each atom is covalently bonded to another atom. These bonds are directional, meaning the atoms can't move around one another, and they're very strong. Also note that this solid will continue to expand in all directions as more atoms are added. Therefore, there's no single repeating molecular unit. This is why it's often thought of as a giant molecule. Likewise for graphite, where we have strong directional bonds between the carbon atoms. However, what sets graphite apart from diamond is the fact that each sheet of carbon atoms is held to its neighboring sheets with a weak intermolecular force. This force is easily broken, which makes graphite brittle, allowing the sheets to slide over one another, as you see when you write with a graphite pencil. This is unlike diamond, which is not at all brittle. It's one of the hardest substances on Earth, since all of our atoms are bonded to its neighbors. So in summary, covalent network solids have high melting points because all the atoms are covalently bonded together. These bonds are very strong and cannot be easily broken. They are also rigid and hard because the carbon bond angles are fixed. The bonds are directional, not flexible. Finally, our fourth type of solid is a molecular solid. In a molecular solid, atoms or molecules are at the lattice points. held together with IMFs. It's the intermolecular forces that set molecular solids apart from covalent network solids. Here we see that each molecule, held together internally by covalent bonds, is held to its neighboring molecules with intermolecular forces, as we see here with this example of water, or here with this example of carbon dioxide. Here, dispersion forces hold each CO2 molecule to its neighbors. Here, hydrogen bonding holds each H2O molecule to its neighbors. Molecular solids can be nonmetal atoms, diatomic elements, or compounds made up of two or more nonmetals. The individual units of these solids are discrete molecules, as we've seen repeatedly throughout this class. As we've seen previously, the physical properties of molecular solids are governed by intermolecular forces. As we see here, melting points and boiling points differ depending on the strength of the intermolecular forces. Benzene is a nonpolar molecule exhibiting dispersion forces only, therefore it has very low melting and boiling points. Whereas phenol exhibits hydrogen bonding, a much stronger intermolecular force, causing its melting and boiling points to be much higher. So in summary, molecular solids do not conduct electricity because electrons are held tightly in covalent bonds. They are localized, unlike electrons in metallic bonding. Molecular solids also have low melting and boiling points because the IMFs holding the molecules together are relatively weak as compared to covalent bonds or ionic bonds. That brings us to the end of this video. Let's review our goals. First, we learned to classify substances as either ionic, covalent network, molecular, or metallic, and then we learned to explain the properties of each type of solid in terms of particle behavior.